Hi everyone. Gas pressure can be measured in atmospheres where the atmospheric pressure that you have around you at sea level is equal to 1 atmosphere. It can also be measured in kilopascals. 1 atmosphere is equal to 101.3 kilopascals. We used to measure pressure with mercury barometers. The liquid mercury would go up higher if there was a higher pressure of gas particles hitting that liquid mercury on the other side. So that pressure would be measured as being 760 millimeters of mercury at sea level. And also another term instead of millimeters of mercury is torr. Those are the same thing. So you can convert between units of gas pressure using unit conversion factors. So you saw in the simulation last time that there is an inverse relationship between pressure and volume. If you take gas particles in a container and make the container larger, then the gas particles will hit the wall less often because there's just going to overall be kind of further from the walls. And so if they hit less often, there will be a lower pressure. So as volume increases, there's a decrease in pressure. There's an inverse relationship between pressure and volume, as demonstrated by this equation, where we have just K a constant. But we would have seen in the simulation that pressure and temperature are directly related. If you increase the temperature of your particles, you will increase the average kinetic energy of those particles. The temperature in Kelvin is directly related to the average kinetic energy of the particles. So when you increase temperature, those particles are going to have more energy of motion. They're going to hit the wall harder, creating more pressure. So pressure and temperature are directly related if volume is held constant. Or if pressure is held constant, and if you were in a flexible container like a balloon, then as you increase temperature, the volume increases. So put a balloon in the oven, it's going to expand for a while before popping. But put a sealed container, a rigid container, in the oven, and the pressure inside is going to increase instead. If you inject some gas into a rigid container, so if you add more moles of gas into, say, a fairly rigid tire, the pressure inside that tire will increase. Direct relationship between those. But if you have a, let's say, bicycle tire, which is not yet rigid, it still can expand, then as you add more moles of gas, the volume will increase instead. So if you have a flat tire, at first you add gas and the volume expands until it reaches sort of that maximum, at which case the pressure inside will increase. Of course, don't overdo it if you're, like, say, filling the tires of a car, maybe. If you overdo it too much, then it could pop. So we can combine all of those equations together into this combined gas law. This combined gas law includes moles at the beginning and at the end. So, or the pressure that's initial and the pressure that's final, etc. But we're not going to use this equation too often. Instead, we use this combined gas law. Please note that whenever you're plugging into temperature, you need to be plugging in Kelvin, because only Kelvin is directly related to the average kinetic energy of the particles, and hence the pressure that comes from them. So if you need to plug in Kelvin, you can get that from Celsius. Kelvin is equal to degrees Celsius plus 273. Now, all of these things are equal to a constant, equal to K. Or you could say equal to R. And then you can rearrange those things equal to R into PV is equal to nRT. That's the ideal gas law. This top equation is for when there's changes in conditions, an initial temperature and a final temperature, an initial volume and a final volume. But this is pretty much for constant conditions. It allows you to know the number of moles of gas that are present in a container or grams of gas that are present in a container. When you are plugging in here, you'll need R. That is a constant. If your pressure is in atmospheres, then you'll want to use 0.0821 liters times atmospheres over moles Kelvin for your R value. But if your pressure is in kilopascals, then plug in 8.31 liters times kilopascals over moles Kelvin. Yeah, and then of course N is moles of gas. So let's say someone asks you to find the number of grams of gas that are present in a container. You use this equation to get moles, and then you go into grams. Let's say someone says the initial pressure in a container was such, and then we increase the temperature. What is the new pressure? Well, that has an initial pressure and a final pressure. That has initial temperature and final volume. So you would use this equation, but you would just cross out V1 and V2. Those aren't changing. There's no mention of them. So you can just kind of cross them out. They cancel each other out. So when you're plugging into PV is equal to nRT, you are just plugging in moles of gas. It doesn't matter whether those are light or heavy gas particles. All gas particles for a given temperature have the same average kinetic energy. You should have seen it in the simulation last time. We had a graph of kinetic energy versus the number of particles. That would have been about the same for the light or the heavy particles. They had the same average kinetic energy because they were at the same temperature. All right, so if you plug into PV is equal to nRT, you plug in N for 1 mole of gas, you can find that if you're at standard temperature and pressure, if you're at 0 degrees Celsius or 273 Kelvin, so that's your temperature. And then if you're at 1 atmosphere or 101.3 kilopascals, your pressure, then you'll get a volume of 22.4 liters. 1 mole of gas at STP has a volume of 22.4 liters. You'll see that in the mole map, which I put up on the lesson plans. It allows you to go from liters of gas into moles of gas of one type of gas, and then convert it to another type of gas using the mole-mole ratio. So you can use a unit conversion factor. You can go from liters to moles of gas, knowing that there's 22.4 liters per 1 mole of that gas. This is only for gases. Don't use this for aqueous solutions, please. You can convert from liters to moles using 22.4 if you're at standard temperature and pressure. But if you're not, then taking a look at the mole map, you'll need to use PV is equal to nRT instead, non-standard conditions. All right, so in the homework today, you'll see 2 extra type of problems you haven't seen before. Like, how do you find the density of a gas? All right, so density is equal to mass over volume. So let's say you're not given mass or volume for, say, the density of carbon dioxide. Well, you can just assume that you might have 1 liter of gas and then find the mass of it using PV is equal to nRT. If you have 1 liter of gas, you can plug that 1 liter in as your volume, and you know the pressure and you know the temperature, you can find the moles of gas. And then the number of grams of gas using molar mass. So assume you have 1 liter, figure out how many grams there are, and that'll give you the density of the gas. You should see that substances that have higher molar mass are going to have a higher density. 1 liter of gas is going to have the same number of moles of gas particles in it as long as you have the same pressure and temperature, regardless of the molar mass. So whether it's light or heavy particles, you'll have the same number of moles of them, but you'll have different numbers of grams of them, and hence different densities. And that's why things like carbon dioxide, which are more dense than nitrogen or oxygen in the air, carbon dioxide will kind of fall to the floor a little bit more. Yep, so you'll see that with dry ice if it ever vaporizes. Okay, and then finally, you may also need to find molar mass. So, molar mass is the number of grams per mole. It's mass divided by moles. So, let's say that you want to find molar mass, and you know the number of grams of gas that you have. Now you just need the number of moles of gas. So you might find the moles of gas using PV is equal to nRT.